Okay, so let's get started. We are very happy today to have Max Tegmark. Max was born and raised in Sweden. He got his PhD at Berkeley in 1994. Then he moved to the Max Planck Institute as a research associate. After that, he moved as a Hubble Fellow to the Institute for Advanced Study as a postdoc. He became a faculty at UPenn, where he became a professor, and after that, in 2004, he became a faculty at MIT. He's also the director of the Foundational Questions Institute, which he founded in 2005. He worked on a wide range of topics in physics and astrophysics, ranging from quantum information to cosmology. He has led fundamental work on the BAO, 21 centimeter, the CMB. He's an author of more than 200 papers, received numerous awards. I won't be able to name all of them, but some of them are the Packard Fellowship. He was named a Fellow of the American Physical Society, and is the author of a recent book, Our Mathematical Universe. So today he will tell us about cosmology, our past and our future. And so with that, it is my pleasure to introduce Max Tegmark.
Thanks, Cora, for that all too kind introduction. It's a great pleasure to be back here again today, meet so many old friends and new friends. I've been asked to talk about cosmology, and I was asked to not just talk about the past, but also a little about the future, which I will do with delight. It's funny how, even though we define our subject often as studying the past, the origins of our universe and its ultimate fate, we spend almost all of the time trying to figure out what happened in the past, and rather little time talking about what lies ahead. And even though, in a way, thinking about the future is even more fun, because this is a problem we can actually influence. I think we'll all agree that things have gotten better during the first 13.8 billion years for life. No, there's a lot more cool stuff going on now than when it was just a bunch of plasma 13.8 billion years ago. And I think we'll also all agree it could get a lot better still. Most of what we see out there is mostly a waste of space, largely uninhabited. There's so much potential for things getting better, even on this planet. At the same time, there's also a lot of potential for us to screw things up in various ways. We'll come back to talk. You know, the future isn't just something that's going to happen to us. I hate when people say, I wonder what will happen. Because, of course, we're the ones making it happen. So we'll talk a little bit about even a little organization we founded called the Future Life Institute, with a bunch of people here in the area who basically think that the future life should exist. It would be cool if we didn't go extinct. And I'll tell you a bit about some fun, concrete things we've been doing to further that goal. But first, let's talk about our past. So I'll spend most about probing our past, and in particular with a technique known as 21 centimeter tomography. I'll talk about, for those of you who aren't so familiar with it, what it is, and then some of the challenges it poses, how we can overcome them, and I'll tell you about a project called Hera, which is currently being built in the Karoo Desert of South Africa, which, if it goes well, can help usher in a new era of cosmology where this technique can be even more powerful than perhaps the cosmic microwave background has been so far, which will be great. That's what I hope will not happen. So, what have we learned so far during the first 13.8 billion years of our universe? Well, we don't know what really happened early on, of course, but we have a very good idea of what happened during the 13.8 billion years since then. We can see much of it with our telescopes, optical, microwave background telescopes, etc. We can probe it with Big Bang nucleosynthesis. But there's still many very embarrassing open questions, of course. What's 95% of this stuff made out of? What's dark matter, dark energy? What's going to happen in the future to our cosmos? What really happened early on? Was it inflation or something else? And what about this period in the middle here, the cosmic dark ages? What happened there? The good news is that there is a vast amount of information out there remaining to be harvested, which can help us address all of these questions. And for all of these questions, we basically would like to do the same thing. We would like to map our universe in 3D better. Look, let me show you how little we've accomplished so far by taking our observable universe here, the micro background, and just looking inside of it. the information that comes from the microwave background, which has revolutionized what we know about the cosmos, it comes mostly from the surface here, which is less than 1% of the volume. And despite all the great work that Daniel Eisenstein and so many others here have worked hard on for the Sloan Digital Sky Survey, this also covers less than 1% of the volume. So the vast majority here has not been properly mapped at all, and it would be great if we could. Most of this volume actually sits at quite high redshift. You can see here 7, 8, 9, etc. How could we map what's out there? We can't, with even the world's best optical telescopes, look at galaxies there because they haven't formed yet. Fortunately, 21 centimeter tomography offers an opportunity to do this. And a number of you have worked hard on this, including Lincoln Greenhill here. The idea is very simple. We have all this hydrogen later formed galaxies, and the 21 centimeter photons get given off whenever the spin flip transition, and as the photon flies towards Earth at redshifts, we know this was a 21 centimeter long photon at birth, so if it comes here at 210 centimeters, for instance, we know it's been stretched tenfold. It came from redshift 9. And if we can just build these really awesome radio telescopes, take this stuff up, we have the potential to map this in 3D. And basically what that will then do is fill in much of the gap between the microwave background really far away and the stuff we can do with other telescopes nearby. This is roughly what we think happened. This is a slide I shamelessly stole from Avi Loeb. But this is an artist's conception. We would love to actually have the data and see how the first stars, black holes, etc., ionize our universe, and how the cosmic dawn really played out. And we would like to answer questions like, what was it really that took place? What was the ionization history, the thermal history, and how can we probe this? Can we measure the power spectrum really accurately here and improve what the microwave background and other things have taught us about dark energy, about dark matter, about neutrinos, etc. Lots of questions. Here's another theorist's view of what we think happened. This simulation is from Tom Abel's group. In the beginning, there was all this hydrogen, which is largely neutral, but then gradually ionizing radiation from the first stars or quasars started ionizing, making bigger and bigger bubbles. We get this Swiss cheese sort of situation, and eventually these Swiss cheese bubbles percolate. Almost all the neutral hydrogen is now gone, and we just have neutral hydrogen left, typically around galaxies. So if you can actually make a 3D map probing this whole region, you just learn so much about so many different things, in theory. What about in practice? Well, in practice, there are 3 big challenges. First of all, sensitivity. It's a very faint signal, so you need really big telescopes, which tend to be very expensive. We'll talk about how we can make things cheaper and really get the sensitivity you need. Then there are foregrounds. Most of the signals one sees here are actually not the ones one wants. How can one deal with that? Finally, calibration, which in some other areas is more of a nuisance. In most of astronomy, you're looking at a bright object against a dark background, so if your calibration is off by 1%, you still get a nice looking picture. But here, instead, we're looking at a faint thing against the foreground, which is 10,000 times brighter. So that you have to try to subtract out. So if your calibration is off by 1%, now you have a problem which is 100 times bigger than your signal. So let's talk about these a little bit in turn. Just like with the cosmic microwave background, raise your hand if you're old enough to remember what it was like when the Kobe maps came out. You remember the very first maps? They looked pretty, but they were so low signal to noise, there was no spot in there you could point to and say, this is real. All you could say is, here's the power spectrum. That's, of course, changed now, but the first detections in the 21 centimeter world will also be like this. We're going to get a power spectrum. I'm going to talk a lot about how to do that and what the foregrounds and such look like. If you can get them, it's been shown by a lot of people, including many here at the CFA, that you can really tell apart a lot of interesting cosmological models. Let's talk about the big foreground challenge then first. So we have this signal we'd like to look at, redshifted radio waves from the distant universe. The cosmological signal is tiny, a very low amplitude, compared to all these foregrounds. We have bright point sources, for example, which if you look at a three-dimensional cube you reconstruct, it looks like striped lines like this, because this is the line of sight direction, the frequency direction. If there's a point source here, you're going to see it at all frequencies, right? Synchrotron rate and diffuse point sources that you don't have in your catalogs look similarly stripy like this, except this time you don't know what the stripes are. Diffuse emission from our galaxy, like synchrotron, looks kind of smooth both in the angular direction like this and along the line of sight. And then there's also the instrumental noise, which can have various complicated properties too. So how can we separate the enemy from our friend? How can we separate foregrounds from the background that we want? Well, the first very basic idea is that the signal we look at, when you take a line of sight to this interesting Swiss cheese Cosmos, of course, there's a very small amount of extra redshifting that happens, say, when you travel 1 megaparsec. So the signal goes up and down very, very rapidly in frequency. Whereas the synchrotron radiation from point sources and from our own galaxy tends to be kind of smooth. So that's a very big help. If you just high pass filter what you measure, you already get rid of a lot of your problem. Because of this, the fact that things look so different along the line of sight, it's very convenient to talk about not the power spectrum with capital D, but to separate the power spectrum out along the line of sight on the vertical direction from angularly across the sky. So there's a three-dimensional power spectrum really of a cube, right? These are the two angular directions combined into one, and this is the line of sight. So I'm going to show you a lot of plots like this. So just to orient yourselves in them, here's some data from the MWA project. A lot of involvement from MIT and Harvard and others. Lincoln Greenhill has worked a lot on this. So far we haven't detected any of the signal. This is noise you're seeing. Problems you have is you run out of frequency resolution. At the high end here, you have problems with foregrounds here that are very smooth in their spectrum. You run out of angular resolution on the right, and you have limited angular extent on the left. And then there's this evil thing here we call the wedge, which I'll tell you just a little bit more about. This is actually sort of the public enemy number one in this field, the wedge. So let me just explain a little bit what it is. If you want to actually exploit the fact that the enemy is spectrally smooth by taking a picture at two different frequencies and subtract them, it sounds like a good idea until you realize that actually the aperture, or the synthesized beam as it's called in radio astronomy, is different at different frequencies. And it's not like for an optical telescope where it's just an Airy function or something. It tends to have a very complicated shape that is sort of the Fourier transform of where your antennas are. So if you take one combination like this and another one and you subtract them, you're not going to get rid of everything. You're going to actually pick up some weird messiness from the beam, which tends to cause this sort of evil wedginess. An easier way to understand this is to realize that these perpendicular and line of sight Fourier thingies have a very interesting and simple physical interpretation. When you build an interferometer, this thing, the power spectrum in the angular direction, is just the baseline, how far apart two antennas are in meters. Farther apart antennas measure things out here, close antennas there. And this is the Fourier transform of the distance, which is sort of the Fourier transform of the frequency, the Fourier transform of the spectrum, which some people call the Kepstrom. So it's going to have units of time, and then you can think of this as just time delay. And what it boils down to within the interferometer is simply how much longer does it take the signal to reach this antenna than that antenna, for example. So it's pretty obvious that if you have a longer baseline, you can get longer time delays also. And you can never get any longer time delay than if the source is on the horizon like this, and things come in like that. So that puts an upper limit to how long time delays you can have. And then so outside of the wedge, you basically expect you shouldn't get any serious foreground problems, because that would, of course, because everything that leaks into your telescope is always above the horizon, and far apart antennas can have a long time delay. Antennas that are twice as close together can only have half as long a time delay. Here's all the evil part. So the Hera project I'm going to tell you about is focusing on and putting antennas very close together, so you get a lot of short baselines. You can work outside the wedge and try to map things here. The LOFAR project, which is a beautiful radio astronomy project in Europe that you all, by and large, know about, has much longer baselines, so they're forced to largely work in the wedge. We wish them the best of luck, but it's much harder. So how do we then try to clean things out? Well, in an ideal world, you can do a bunch of math and blah, blah, blah with matrices, the kind of stuff that I love doing late at night, and most other people might view it as like the perfect sleeping pill. I'm not going to bore you with the math, but let me just tell you why to bother with these sort of optimal data analysis tools by giving you a little example here from a grad student Josh Dillon made. Let's take a signal which is just a one-dimensional time series. Can someone tell me what song this is? Yes. So that's how it actually sounds. Now let's add some foregrounds and noise. Let's add some. So this is the power spectrum of it in one dimension. Let's add some instrumental noise. It comes in mainly a high frequency. You can hear that in the background there. Let's add in some foregrounds. They tend to be pretty smooth, right? So that's going to be mainly low frequency stuff. I don't know if you can hear the hum there in the background, and it's dominating the amplitude of the whole thing. That's why it sounds so faint now. So what can you do about this? Well, the naive thing you might do is say, let's just FFT this thing and throw out this part and that part and just bandpass it and keep the part that seems signal dominating. It did better, but it's still not great though. If you do this sort of matrix jazz, it's not going to do this sort of sharp cutoff. It's going to do it more optimally, and it sounds like this. Still nothing that a music lover would be proud of playing for their friends, but it's definitely better, right? And this is exactly what all this fancy matrix jazz is actually doing to our signals, except it's in 3 dimensions now instead of 1 dimension. But this is the idea. You simply look at the statistical properties of your signal and your noise, and then you figure out the optimal way to do all this, and then you do it. That's all you need to know about it. There's a bunch of boring math to go with it, which I'll skip over. There is a catch, which is that when you do it optimally, the time to do it is longer than the age of our universe. So Josh Dillon, a grad student of mine, who's now gone off to do a postdoc at Berkeley, worked very hard on figuring out a way of doing it faster. Eventually he found one, and it's complicated. I'll spare you the details. It does it in sort of n log n time, but it works. That's all we need to know about it. Let's skip through the map quickly here. And this is just to show that it actually works. This is how long it would take for a 1,000,000 voxel data cube with the old method. And you can see it actually takes sort of feasible amounts of time now. This is very relevant because the data is happening now, and we want to actually analyze it, not just stare at it. So let's talk a little bit about experiments and where they are. This is a very cool field, so it's an exciting race between a lot of different teams around the world. I'll tell you a little bit about Meteor, Omniscope, and Paper, and MWA, and Hera. The Chinese project seems to unfortunately have imploded, as far as I can tell. This one is already pretty much done. So the first application we did of these fast techniques were with the MWA survey, where there are a whole bunch of these tiles of antennas out in Australia. Right now there are 128, and I'll spare you the details, but we didn't detect the signal. We were just able to put upper limits. They were the best ones at the time, but you can see the upper limits are still far above where you sort of expect the signal to be by quite a bit. The Paper project in Berkeley has the best limits so far that are published, led by Aaron Parsons et al. And they still haven't seen a signal, but we're getting tantalizingly close now. And what's nice is that the data is still showing no signs of being dominated by systematic errors. We seem to be able to clean out the foregrounds. It's just that the noise keeps going down as the experimentalists work harder and harder and build bigger and bigger things. And the computers are able to analyze the data still with these kind of techniques. So how can we scale this up and actually detect this wonderful signal? How do you build a much more sensitive telescope? Well, just think, let's build a bigger one. What do you need for a really big telescope? You need a really big budget. But how big? That's an interesting question. Right? For a single dish telescope, the cost grows much faster than linearly with area, of course. And if you ask a friend to build you a radio telescope that's 1 square kilometer and can point, no, she's not going to be your friend anymore after that. So what all these groups have done is switch to interferometers, where you instead build lots of small antennas and have computers do the work of figuring out what the sky looks like. Problem there is that the cost grows like the area squared, because you have to correlate all pairs of antennas. So like n squared. Unless you put the antennas in some sort of regular grid, because then it turns out that you can use just fast Fourier transforms for doing all the math. It goes like n log n. So we wanted to explore, Matthias Aldeaga, back when he was here at the CFA, and I, whether we could actually make this work. So we built a little tech demonstrator, and we figured if we can make this work, then we can incorporate this technology into something bigger like the Hera project I'm about to tell you. And for those, raise your hand if you remember Matthias Aldeaga. So he's a very theoretical guy. So this is a very compromising picture. He has actually touched metal. So next time you see him, you can accuse him of being an experimentalist. We started on the roof by building at MIT, and then we went to Green Bank, did a bigger thing, and then we went and built a series of things that we deployed up in northwestern Maine in this great metropolis of West Forks. I'll just show you a little video of how to build a radio telescope in 2 minutes. And that's Joanna, who is sitting there in the audience, just so we can embarrass her. So we had lots of fun with this. The students also liked it because we would drive up in this van which contained all our stuff and then spend an afternoon setting everything up, and then the next day half of us would take data while the other half went whitewater rafting. And then the next day the survivors would take data while the rest of us went. And a lot of fun was had, and best of all, it actually worked in the end. So this is a completed and finished project now, and we've taken the technologies we developed here and incorporated them into this much bigger project, Hera, which we're doing together with a bunch of other universities, and I'll tell you about it now. One very useful technique that came out of this, which is used now in Hera and also in the paper project, is to be able to calibrate all your antennas automatically in real time. Calibration is usually a sort of dark art which involves a lot of manual work, and you have to make some model to some level of what's on the sky and figure out how many percent up or down each amplifier has sort of fluctuated, and what phase shifts there are, because some wire is a little longer than another or whatnot. And if you have vast numbers of antennas, it would be so nice if you could just automate that completely and have it done in real time also, so you immediately find out if something is broken. And that's exactly what my grad student Jeff Zheng managed to do. So I'll skip through this quickly. The basic idea is, first, we use satellites that fly overhead to get a rough sense of, to get a very strong signal that we know about, just to get things roughly right. So if you look in, if you take any pair of antennas, the signal that comes over time, at every instant you have a complex number you measure. It comes out of the correlator. So you can plot it in the complex plane like this. And then it'll move around in some funky shape over time. But if it's a satellite, you know it should, in this case, make this green shape. So you can ask, what complex number can I multiply the blue data with so that it falls on top of that? Nothing profound about this at all, but it just gives you a good starting point for the novel thing that he did, which is to use the idea of redundancy. So basically, if you have a radio telescope that measures, if it has two antennas, this one will get signals a little sooner than this one from some object over there, etc. Right? If they're separated by 10 meters in the east-west direction, the correlation, the complex number that comes out of them should be exactly the same as from any other pair of antennas that are also separated by 10 meters in the east-west direction. So that's very nice. If you have a regular array of antennas in some square grid, for example, you'll have lots and lots of pairs which all should be measuring the same thing, but don't, because the cables are a little bit off in length, and the amplifiers fluctuate in time and stuff like that. So for each antenna, you want to figure out what complex number should I multiply it with at each time and each frequency, so that all these things that should be the same are the same. And you can solve all that math without assuming anything at all about what's actually on the sky, which is awesome. So just to show you how it works in practice, the data that comes off, the raw data looks like a total mess. All the green squares should lie right on top of each other. This is the complex plane, real imaginary part. After you do a rough calibration with the satellites, you see the blue squares kind of lie near each other if you squint a little bit, and the yellow circles kind of, but they're still not on top. And then we use this very cool algorithm that he developed, which can be run in real time, and it just solves all these equations, and boom, all the blue squares lie exactly on top of each other, etc., etc., etc. And this works so well that when we apply it to our real data, we can just, as a function of frequency and the time, not just figure out what all the antennas should be, we get a chi-square that just says, is everything okay, or is there something that's wrong? And we can just automatically flag as bad anything where the chi-square is not good, and we can completely automate the whole data cleaning process. So this is what, for those who are radio astronomy buffs, this is the phase you should measure between two particular antennas as a function of hour and as a function of frequency, for instance. And when we mask this with the bad times, it should look like this. It actually looked like this. So there were actual data. And so it works so nicely that the paper folks who were initially working on this competing project said, hey, we love this. Can we use this too? And now they're also using this algorithm. And in the last power spectrum paper that has the best limit so far on 21 centimeter, they're using this code, and we're happy to give it to anyone who wants it. And it's very important to have real precision calibration. The precision science that comes out of this stuff is only as good as the calibration. So to be able to do this, we decided that the Hera project is also going to have all its antennas in a regular grid. This also looks different from a lot of other radio telescopes in that they're all scrunched together. The antennas, they're very close. That's because of this, to stay away from the wedge. You want short baselines, not long baselines. Then you see they're in a hexagonal grid, and we can also do this Fourier FFT faster correlation. There are a lot of advantages of this. It's a pretty big and ambitious project, covering about 0.1 square kilometers ultimately. So far, the NSF has funded this much of it. But the good news is we've already built now 19 of these antennas. They're 14 meters in size each, and they're working. So we're putting in a proposal for the full 15 million, which is what it's going to cost to try to build the whole thing here And if we can get that, we're now in a position that we can say that there were all these things we weren't sure that were going to work, but now we built them and they actually work. We even have the software and the data to prove it. And we're hopeful that we will be blessed by them or the Moore Foundation or some combination of the two. And this is a telescope which will map this stripe here with such great precision that we should be able to see the cosmological 21 centimeter signal for the first time, like falling off a log, which would be very, very cool. So if we do that, then what cool things can we learn from it? What kind of science comes out of this? A lot. First of all, from just measuring, for example, we can measure how ionized our universe was as a function of redshift, as a function of time. This is a forecast for how accurately we can measure this with Hera. And there are a lot of exciting constraints, of course, from Peterson, from WMAP, etc., etc. There's a whole new level of precision. So it'll be very, very, very nice if we get it to work. Another cool thing you can do here, this is work by Aaron Emo Weiss, grad student at MIT, shows how you can put strong constraints on the temperature of our universe or the spin temperature. One can also, if you build any particular cosmological model of how the Swiss cheese process went and parameterize it with some parameters, you can put constraints on them. The details don't matter here. All you should note is that you get eventually, when you put in Hera, much tighter constraints than you could before. So we're very excited about this project. And this is not something 10 years from now. We're building things now. If it can get funded, we should have some really awesome data within years, not decades. And I think the whole field of 21 centimeter tomography really holds a lot of promise. It's kind of like the microbackground in the old days, before COBE, for those of you who raised your hand there, in that it's obvious the signal exists. Everybody knew that there was fluctuations in our universe, but it wasn't clear whether you would ever be able to really see it, because foregrounds and tech problems, right? But then once COBE demonstrated that you could, there was this huge surge of activity, and then we got all these other experiments and WMAP and Planck and so on. If we can do something like this would be the WMAP of that field, and really look, here is the signal, and then moreover show how one can do it very cheaply. This can be scaled out to give amazing precision cosmology, which I think would be pretty cool. So that brings us to the end of the first part of my talk, the past. We talked about what we've learned about the first 13.8 billion years and this cool new technology for studying it. What about the future? Let's spend the remaining 20 minutes or so on that. I'm an optimist. That's why I usually look quite happy. I think there's great potential for awesome things in the future, not just in our personal lives, but also for our civilization as a whole. Our cosmos, we've discovered, is so much vaster than we thought. There's so much more potential, of course, for great things to happen. But of course, things could go great, but there are also all sorts of problems that could happen. I'll come back and talk about some of them and what can be done about them. If you go read books or science fiction or talk to scientists, you'll hear all sorts of different ideas for what's around the corner in our future. Some people are very optimistic and talk about all the cosmic awesomeness that could happen, how life can flourish throughout the cosmos one day. And then there's no shortage also, of course, of people coming up with more apocalyptic scenarios about various ways in which we could mess up. So in the book that Cora mentioned that I wrote, Our Mathematical Universe, I decided to summarize all the things that people like to worry about, but organize them by sorting them by how far into the future they would be most likely to screw us over, okay? From least urgent to most urgent. And it's kind of interesting, actually, that all of the most urgent ones are things we cannot blame Mother Nature for. They're things we can only blame ourselves for, that we're causing with our technology. So let's start, on the flip side, the optimistic note is that if we can avoid wiping ourselves out, we actually have much more time to take on these other challenges. What about the cosmocalypse? Are we going to end with a big chill, or a big crunch, or a big rip, or a big snap, or death bubbles? I don't know, but none of those things are going to happen anytime soon. And if it's going to be the big chill, actually, we have a lot of time. especially if you move to an M star, and there are other ways of living in more than hundreds of billions of years. More urgent is, of course, that the sun is going to get too hot already a billion years from now, and it's going to vaporize the Atlantic Ocean, which will put a bit of a damper on the beach season here. But there's a very nice technical solution that's been proposed, and there was a nice paper on the archive recently, but Avi Loeb just told me that Gerard de Hooft had similar ideas earlier. The idea is that you fly out with a rocket and you deflect an asteroid, come near Earth. You do it carefully so it doesn't hit Earth, because that's not going to make you friends. But you make it go close enough to Earth that its gravitational pull just tugs us out a tiny bit, a slightly large orbit, then it goes back again, slingshots around you, retune its orbit, and it comes back. After many, many passes, in only 300 million years, you can move Earth slowly out to large orbit and basically keep the temperature constant for billions of years, which is awesome. And we don't even have to start this for 100 million years. So that's good news. We can last up. And then asteroids, again, obviously, the question isn't if they're going to get us, the big one, the one that took out the dinos 60 million years ago, but how long it's going to take. But there again, obviously, you all know if we have good advanced warning, it's a pretty easy thing to deal with. And you don't have to fundraise for the asteroid deflection mission. You just have to fundraise for the science to find them. Because if you find one, you can figure out exactly when it's going to strike, and you figure out how Earth is rotated exactly then, and you realize, oh, it's going to land on Houston. And then you go do a little fundraising campaign in Houston for the deflection mission. Surprise! It's going to go real easy. So that's certainly doable. And in fact, all these ones have the property, I think, that if we can last that long, then we have plenty. We will be able. There are easy technical solutions. Even we today have thought about that will probably work. So let's talk about the more urgent ones, the self-inflicted ones. Okay. So I decided when I wrote the book to give us humans a grade for Risk Management 101 for how we're doing so far. At first, I was thinking maybe I should give ourselves a B+, because we're still here. Could be worse. But that's kind of the standard perspective. If we just think about the next election cycle or our lifetime, we don't know what the probability is that we're going to go extinct in any given decade for some stupid reason. Some people think it's very unlikely, maybe 10 to minus 4. Some think it's more likely, like 10%. But regardless of where it is in this sort of range, it's a pathetic strategy if you want to last for 1 million years, let alone a billion, right? So I decided to give us a D-. And just to emphasize why I gave a D-, even though I'm usually a pretty lenient grader, let me just ask you this question. Which one of these two people is more famous? And before you answer, let me just also ask you, which one of those two people should we all thank for us being alive here today and having this conversation? Because he single-handedly stopped the Soviet nuclear attack during the Cuban Missile Crisis. I'll give you only one hint. No, so that's pretty lame, I think. That issues like that aren't. We pay so little attention to these things that my children never even learned about him in school. There's no statue over him. Nothing, And to further emphasize how reckless we tend to be with major threats to our civilization, let me just give another little example to do with nuclear weapons. So we've been so flaky about this that we haven't even done the research looking into the physics of what would happen very carefully. It's usually done randomly long afterwards by some random people. First, when people built nuclear weapons, they thought the most dangerous thing was just getting literally blown up. Right? It was only later that people realized actually, this fallout stuff isn't so great. And in fact, less than half of all the people who have been killed by nuclear bombs so far were in Hiroshima and Nagasaki. Most of the deaths are because of the nuclear tests from the fallout. And the US government has already paid out over $2 billion to settle lawsuits about fallout. So then people thought, okay, we screwed up, but now we understand. The most dangerous thing is the radioactivity. And that went on and on and on until the 80s, when people realized, see, there's something else which is even worse about this that we just all together forgot about. And at the peak, there were about 63,000 hydrogen bombs on Earth. Now, there are only about a quarter of that many. And it's been steady for the last 10 years or so, about 16,000. Why did we decide to scale back by 3/4? Most people I know think it's because the Cold War ended. That's the sort of mantra on the street. But actually, if you go look at the data, that doesn't really make sense, because the biggest cuts were actually agreed to before the Cold War ended. And if you go ask the people who agreed to them, namely Ronald Reagan and Mikhail Gorbachev, why? They say in their quotes, this was because they learned about nuclear winter. How did this come about? Well, just because some random scientists in New Jersey and in Russia and so on discovered that, oops, there's this other thing, that if you have a nuclear war between the US and Russia, our nice little planet will look more like this afterwards. And then the soot spreads a little bit, and that won't be so great. So that both Reagan and Gorbachev realized that even if you technically win a nuclear war by launching all your missiles and not a single one comes back, it's actually not mutual assured destruction, it's self-assured destruction. Sad, you just shot an own goal, because now this soot comes over your country too, and everybody is basically equally screwed. And then, as if that weren't bad enough, it turns out that those calculations back in the 80s, which had this big positive effect, were done by a computer that was less powerful than this. Okay? They were recently redone, though, on today's supercomputers, with a much better software that's been developed to study global climate change. And it turned out there was a mistake in the old ones. There's still a big uncertainty in a lot of the modeling, so we can't really put any upper bounds on how bad it is, which is unnerving, but it seems like the old calculations were too optimistic, and it's actually quite a bit worse. So this is from a more modern calculation by Alan Robach at Rutgers. And this just shows you the mean change in temperature in Celsius the next year after a typical all-out war. As you see here in the American breadbasket, like Iowa, places like that, typically 20 Celsius drop. Also in China and Russia, you get more like 30, 35 Celsius in parts. Temperature drop. So what does that mean in plain English? It's the difference between this and this, right? So without doing a lot of fancy schmancy analysis, it's clearly not a very great thing. And moreover, they realize that this typically lasts for not 2 years, but about 10 years, the effect. So if you get rid of most of the food production for 10 years, it seems like it would be kind of a good thing to avoid. So why is it that we spend so little time and effort as a civilization trying to avoid these kind of pitfalls and making sure we use our technology for good? When I ask people, sometimes they say it's just we don't have enough money to do things about this. The economy is tough, we need to worry about jobs, whatever. But if I like numbers, so I decided to look at some numbers. There is an organization right here in Cambridge, Union of Concerned Scientists, which has perhaps the biggest budget of any idealistic organization that tries to help reduce these kind of risks. This is their budget, 20 million a year. Let's shrink that down to a few pixels, okay? And see what other indispensable things we spent money on last year. Cosmetic surgery, 10 billion, air conditioning, 20 billion. That's only for US troops, not for the rest of us. Smoking, and the military I couldn't even fit on here. So I have to shrink. So it's clearly not that there's not enough money. And another argument I sometimes hear is, well, it's just reckless and dumb to spend money mitigating risks that nobody has proven for sure are real risks. You sometimes hear that about climate change. If you can't prove for sure that this is a problem, let's not do anything about it. It sounds kind of compelling until you start to think about it more carefully, right? Until you think of this scenario, for example. Suppose you're in a store buying a stroller for the baby of a good friend of yours. And the salesman says, hey, I have this really robust stroller here for $49.95. It's been on the market for over 10 years. Never been any safety issues with it. And then I have this model. I know it's a little flimsy. And I know you may have seen some news reports about it sometimes collapsing and crushing the child and all. But nobody's ever been able to prove, at least in the court of law, that this was due to any manufacturing defects in the stroller. It's 20% off. Wouldn't it be irresponsible for you to spend an extra 20% on an mitigating an unproven risk? Which one are you going to buy? Well, if you're willing to spend the extra money just as a precaution for one child, then why not for all future children and all future generations? So this was a bit of the motivation for a bunch of us to start this little organization, the Future of Life Institute. You can see, we basically want to support research and attention paying to the issues that are going to help increase the probability that the future of life will exist, which seems pretty non-controversial. There are a bunch of us here in Cambridge. It's me, my wife Maya, Vika Krakovna is a Harvard grad student, Anthony Aguirre is an astrophysicist many of you know, and Jan Tallinn, you know him if you've used Skype, because he wrote Skype together with a few others. And then we have, I'm fortunate to have a bunch of scientists who are interested in various technologies to make sure they're used well. George Church here at Harvard, and of course and Christoph Koch, sorry, are very interested in biotechnology. We have some of the world's artificial intelligence pioneers there. We have a lot of physicists and others, and also some people who are really into science communication. And we were a pretty cheerful bunch, so we didn't want to spend time whining about stuff. We wanted to just spend time doing things that we felt were constructive. So so the basic idea was, we humans, when we do science, we gradually figure out more and more about how the world works, and then we use this knowledge to create new technologies, which we can use for good or to mess up. And in the past, the technologies we've invented have usually not been very powerful. They've been things like fire, which are of course double-edged swords, but it was perfectly fine to just go ahead and learn from our mistakes. We screwed up with fire a bunch of times, and then we invented the fire extinguisher, and done. Okay, the fire escape too, and a few other things, but it basically solved the problem. But with more powerful technology, like nuclear weapons, like synthetic biology, and maybe in the future superhuman artificial intelligence, if we can ever build that, we would kind of prefer not to learn from mistakes. We would rather get it right the first time, right? Because it might be the only time we have. So we've done a lot of brainstorming about asking what kind of research could we do now that would help our society get things right from the get-go. So I'll just give you one example of something we did. We last year there was since Stuart Russell literally wrote the textbook on artificial intelligence, there's been a lot of interest in a lot of progress in that field recently. We wrote a letter, Stuart Russell and I, and Frank Wilczek and Stephen Hawking, which immediately got bastardized by all the British tabloids as robots will kill us all, complete with Terminator pictures and stuff, which is pretty dumb. But there was a lot of discussion last year about this, and then Elon Musk, you might have seen him giving some quotes in the newspaper, and Hawking. But the really interesting thing is not, of course, whether you should worry or not. The really interesting thing is, what can we do now that can be helpful? So we organized the first ever conference of. We managed to bring together artificial intelligence researchers. We had a conference in Puerto Rico in January this year. We had almost 100 people. Many of the top people in AI, both from academia and also from industry, like Google, DeepMind, and others, to talk not about the question of how you make AI smarter, but how you can make sure it's beneficial. And it was a really cool conference, because even though a lot of people in the media wanted to portray this as sort of controversial, it wasn't really controversial at all once people were on the beach and had their martinis and stuff like that. Everybody agreed that there's a great potential for AI to be good, like for any technology, and there's also plenty of potential to screw up. And it was really interesting to just brainstorm up a list of concrete research projects you could do, questions that you wanted to answer now, and then make a list of projects and then get people to do them. And a nice thing was that Elon Musk was there at the conference also, and he said, okay, I hear you guys, you have all these projects you want to do. Let me give you 10 million reasons to do them. So he gave us 10 million, and we launched this competition that we opened up to everybody in the world to apply for grants to do this sort of work. You can go on the website, and there's this long technical document with all these possible projects, and there was an open letter that a bunch of people signed saying that's good. And at the end of the day, skip over that. At the end of the day, even though the deadline was very short and the topic was sort of null, so we weren't sure if there would be much response. We got 300 teams from around the world with AI researchers putting in awesome proposals. It was really cool, except it was sort of painful to get all the experts to review them. But in the end, we did this, and 37 winning teams were just announced. I actually pull them up here. In fact, there's even a guy here at Harvard who you probably don't know, David Parks, because he's an AI. Got 200,000 to do stuff. And so the conclusion of all this was, there's an example of a technology which has huge potential for good, of course. Everything we like about civilization is a product of intelligence. If we can amplify our intelligence a little bit with machines, we can use it to figure out how to cure all diseases and do all sorts of other cool stuff. But of course, it can also be used to cause in all sorts of ways it can cause problems. And these people all agree here that, hey, let's try to get it right. And now this debate has sort of shifted from arguing about, whining about it, or arguing about whether to worry about it. These 37 teams actually doing useful stuff. And we're quite excited about that. But that's just our little organization. We're hoping to basically look at all the powerful new technologies and ask the same question. What can we do now to make sure that they're used for good and to avoid the pitfalls that come with them? And this little experience that I just shared with you here of doing something as audacious as, some physicists trying to organize a conference for AI researchers, it sounded completely doomed at the outset. It's like if some chemist invites you to an astrophysics conference, you would be like, if I want an physics conference, I'll organize my own, thank you. Right? It seemed kind of impossible. But the fact that we were actually able to do it, and then it even had all this nice outcome, and the whole thing took only about a year, I felt it was very empowering, and it showed that we shouldn't think of the future as something that's just going to happen to us. That we just have to sit there and passively wait for it. A small number of people can actually make a very big difference, especially super talented people like you guys. So when you look at the future and the great opportunities there are there and the challenges there are, I would like to end by just saying that, even though we humans have are small in the physical sense, we really have great power not only to understand the world, which is what you usually do as scientists, but also to improve it, to use this understanding to figure out what the pitfalls are and how they can be avoided, and then to persuade other people to actually avoid them. So I would like to end on this optimistic note and say I think we live in a very, very exciting time where after 13.8 billion years of cosmology, we have reached the point where we humans have learned so much about nature. We now both have the technology for the first time we're on the verge of having technology that can basically solve all our problems and make life even more awesome, or wipe everything out. So we're at this fascinating fork in the road. Which way is it going to go? Well, you have a great ability to influence this. So let's make a difference. Thank you.
Are there questions?
So you make your mention this, but I cannot remember. What range of redshifts we are here covered?
Hera is looking at redshift of 7, 8, 9, 10-ish, which is basically the epoch of reionization. But the basic technique of 21 centimeter tomography works anywhere where there's neutral hydrogen, all the way up to redshift 50 or so. So there's also other experiments, the CHIME experiment, the Canadian project, for example, which is looking at redshift 3 and 2 and 1, where you mainly see it around galaxies, and it's going to teach you wonderful things about dark energy. I'm for doing all of this and exploring the full redshift range.
I was disappointed to see that your ambition of making a difference were limited just to Earth. You didn't talk about affecting the universe.
Oh. Let me see if I can undisappoint you then. That's why I snuck in the Hubble field here, because we of course
make a difference in the universe.
Oh yeah, I mean, we obviously don't know what the situation, how much life, how far it is to the nearest neighbor intelligent civilization. We all know about the Fermi paradox. It seems to be pretty far. Most people I know sort of just take for granted that there's some sort of, we live in a sort of Star Trek universe where there are all these super advanced civilizations all over the place somehow. We just haven't seen them yet because there's somehow just so many stars. I give a quantitative estimate in my book, which I won't bore you with here, but my own personal guess is that it's actually that the probability is more than 50% that the nearest life that has telescopes is outside of our Hubble volume. And that might be wrong, but suppose it's true that most of the life in our universe is more like cows and bacteria and stuff like that, which you will find with the exoplanet surveys. But suppose that's true, then you can really make a huge difference here on Earth, right? Because that means that if in the distant future, much of our future light cone is teeming with life, it came from here, right? We made all the difference. We don't know, of course, what those descendants of ours are going to think about us, but they certainly aren't going to think we were insignificant.
Yeah.
So in the future, astronomy is really an applied subject.
I think it should be viewed as an applied subject even today, because I think just looking at ourselves in the cosmic perspective really does change, I think, how we deal with things on this planet. I mean, I had I'm fortunate to have lunch with an astronaut a while back, and he just mentioned that the first time he saw Earth from space, it just really moved emotionally and felt that, his priorities permanently shifted towards feeling, hey, let's think a little more long term, and I hope that people who study our field of astronomy and cosmology will be able to come to similar insights even without actually flying to the space station, just traveling with their mind. Charles, you had a question.
Yeah, it had to do with the politics of mitigating risk.
Yeah.
Like with nuclear weapons, and basically the whole issue is what you don't do.
Yeah.
Right? And if you only have 2 major states or a small number of major states, because it's a big industrial process, you can actually imagine the control problem with a few negotiations. But with AI, this is going to be growing up in many places, thousands of places. Do you have any sense of how you persuade everybody, including the people you haven't met and the people who think you're a jerk, not to do something?
So let me split that into 2 parts. Before tackling the harder question about what to do about it, there are even more basic questions which also haven't been answered. It's like, suppose we're discussing nuclear weapons in 1920, right? The first question people would have is, why should I even believe that these things you're talking about are possible? Can you show me like one picture of an actual nuclear explosion? And we'd be like, sorry. And people would have no idea about the yields or the costs or anything. Right now, if you talk to the world's leading AI experts, like some of them think they will never be able to make machines smarter than humans. Some think it's going to take these hundreds of years. We did a poll at the conference. The median, some thought it would be 20 years. The median was about 40 years from now. But there's a huge uncertainty, first of all, in that. And then there's also a huge range in what they think will happen if we get there. There are some people, some very serious scientists who think that in AI, who think sort of by default going to be awesome. There's absolutely nothing to be worried about. And then there are other scientists who think it's almost by default going to be doom. So clearly, very basic questions like that, it's very helpful to start addressing them before one makes any policy recommendations. Is it, for example, how hard is it to make systems that can recursively self-improve themselves and get smarter and smarter, but still keep basically the same goals? If someone can make some proof that that's possible or that it's impossible, it will completely change much of the debate, right? So I think right now what everybody agreed at the conference is, since we're talking about something that's probably decades away, now is not the time for panic or to ban things. Now is the time to ask these hard questions and trying to figure out, what's the science of this? What can be done? What cannot be done? What is dangerous? What is not? And maybe in a few years when I'll be in a position to start answering actually your real question of, are there certain kinds of AI that are much safer than others? Should you try to encourage this kind of work, not that kind of work? Not now. I mean, there is an encouraging precedent in biotech, right? The George Church, who knows George Church? Yeah. Let's talk about the Silomar conference of 1973. when recombinant DNA was first figured out, and people were able to start messing with human germline, and first a lot of scientists were afraid of even talking about this because they were afraid it was going to cut their funding or lead to regulation. But then they got together a bunch in the Silmar at this conference and talked about it openly, and they realized actually there are some very sensible things we could just adopt as guidelines, and they did. And then the NIH said we're only going to fund people who abide by these guidelines, and then the military said we're also only going to do things that abide by this, and it basically became the thing that everybody did, and they haven't had any serious problems since. So that sometimes this sort of foresight can actually work. I'm not saying I'm sure it'll work, but it's certainly more likely to work if you try. And it's what I think is clear though is that if we do succeed one day and really figuring out how our brain works, or not figuring it out but building something which can do everything the brain can, it's going to be the most important. It's going to be the biggest event ever to happen to humanity, of course, because then we can stop doing science. You can tell your computer to figure everything out for you. We don't have to invent anything more either, because you can tell the machines to invent things for you faster. And so it's either going to be the best thing that ever happened or the worst thing that ever happened. And the one thing one can say for sure is, it's the kind of thing you would like to think through first. And it might, the questions that you ask, Charles, are so difficult, it might take 20 years to answer them, or 30 years. That's why it's good to start researching the questions now, not the night before someone switches it on. That make sense?
Yeah. You spent most of your time on the past and a relatively small fraction on the future, but the questions have almost all been directed to the future part of it. I would like to redress the balance slightly.
Good.
And ask a trivial question about the past. I'm old enough that I lived through the missile crisis, and I was in fact grown up by then. I never heard of the person who paired with Justin Bieber, nor do I have the slightest idea how he single-handedly prevented anything.
Let me tell you about this then.
So
you should not feel bad about not having heard about him, because nobody had heard about him. You should not feel bad about it, because nobody heard about him for many, many years. The Russians didn't tell anyone, and it was classified. But what happened was, the Soviet Union had sent 4 submarines, which the Americans did not know were equipped with nuclear torpedoes. Okay, and then the Americans found the submarine that he was in, and decided to drop depth charges at it. They were only practice depth charges, which weren't supposed to sink it. They were trying to make the submarine just come up to the surface. What the Americans didn't realize was, first of all, these guys had no radio contact at all with Moscow, and their submarine was failing. They were almost out of battery, and the temperature was rising, so it was like 50 Celsius or something on board. Terrible conditions. They were all very, very stressed. And so then I thought the fact that they're dropping depth charges here in international waters probably means that the Third World War has already broken out. And the commander of the submarine decided to launch a nuclear torpedo against the U.S. fleet that was depth charging them. And I don't know for sure if that would if there had been a nuclear explosion that sank a bunch of the U.S. warships, if that would have cascaded into an all-out war or not. No, it's anyone's guess really, but it certainly is not a very, very relaxing situation, right? So the reason they did not launch the nuclear torpedo, even though the captain of the submarine wanted to launch it, was because they had a rule that if they were cut off from Moscow, the top 3 commanding officers had to all agree. So there was another guy who also said, yeah, let's launch it. And then Vasily Arkhipov said, niet. And so they didn't launch it.
What was his reasoning?
I've been trying to read about this in the declassified papers are out, and haven't been able to find out very much. I think he just had a different statistical assessment somehow, that somehow that could be another explanation for what was happening, that it maybe wasn't World War III. So in the end, they decided to surface the submarine. This was very humiliating for them. So the U.S. warships came up, But of course, it was international waters, so that the Americans wouldn't have any right to do anything. The Americans also knew that if they sunk the submarine there, that would be very likely to start the Third World War anyway. So in the end, they were allowed to just go back to Russia. And he's dead now, so we can't ask him either. But if someone finds out more about this, I would love to know. But this is just an example of how I think, in hindsight, we were more reckless than we thought with things. And if we keep playing Russian roulette, every century or every 20 years or something, we roll the dice and do another equally reckless thing. You all know how to do your probabilities. The probability we succeed to survive for n years drops exponentially with a half-life of ballpark of however often we do this. And so it's not a very good long-term strategy, even if we got lucky that time.
Okay, well, if there are no more questions, let's thank
Let's thank you.